Our final speaker is Michael Smith. He is a principal member at Sandia National Laboratories. He previously earned his PhD at Brigham Young University for his work on instance-level metalearning. In his current role, his research focuses on explainability, credibility, and validation of machine learned models in high-consequence applications and their effects on decision-making.
All right. How do I advance slides? All right, thank you. Pleasure to be here with all of you. And Shihan's work leads right into this. We're taking basically a system-level approach of how to assess systems that have some machine learning or AI-enabled components that are within them. Of course, let's see. Where's the button? Oh, I see it. So we're going to talk about this just for a minute. Of course, once we have these data-driven models, they differ in how we need to test and evaluate them and actually do an assessment with them. So I'm going to talk a little bit about what is machine learning, why do we care about this, and why is it different than our typical software or cyber systems, and then talk about the methodology that we put around essentially the traditional red teaming methodology for assessing these type of systems. So of course we've seen a lot of these things, but these are just a couple stats to reiterate and really drive home the point. Machine learning and AI, of course, is growing exponentially since about 2015, which is when deep learning essentially broke through a barrier. We have seen exponential growth everywhere. So these are the numbers of conferences and conference attendance. You can see that more than almost 100,000 people are attending these conferences, trying to learn as much as they can throughout the world. Google, of course, is one of the first places that pioneered this technology. And I list it here just to show that not only how much money and how much they're trying to drive into this, but the different kind of the diversity set of projects that they're putting machine learning in. So we can see Android apps, but drug discovery in their Gmail. Of course, there's YouTube, speech translation. It's essentially all over the map of where this, and we can encounter machine learning and these deep learning technologies. Of course, it's not just academic or just Google. The number of investments going into machine learning and AI right now is also growing exponentially. A little bit behind to 2015, right? Once we started to see success, a lot of money was starting to get poured into this. And again, showing the different applications of where this is being applied, of course, is very broad as we try to test and evaluate these different systems that span these applications. And again, just to reiterate home, right? We see it every, in case you're not aware of this, right? Machine learning is ubiquitous in almost everything we do. If you go shop on Amazon, you see it every day. If you do Netflix or any other type of streaming video or media, all these recommendation systems are driven by AI machine learning. Nowadays, we might not even call it AI anymore because we're so used to it. But then we can start seeing self-driving cars, of course, Siri, and then smart homes, right? It's integrating not only into our recreational, but to our very lives of how we live and what we choose to do. So let's talk just a little bit about what is ML, and this will help drive about why is it different than how we need to assess these systems. If you look at this top picture here, traditional programming, we have a couple different inputs. Generally, we have what should our input be, what's our data, and then we have some program. We write a program, we know what it should be, and then we get some output out. Machine learning changes that in a way. Instead of putting in the program, we say what's our input and what are our outputs. You can think about these are pictures. In the image I have here, we have a whole bunch of apples, and we label these are all apples. The machine learning algorithm then comes up with the program. So it's a little bit of a paradigm shift here in what is the code and what is it doing. And we've alluded to a lot of the times we don't understand what this is. Of course, this is called supervised learning. There's also a paradigm called unsupervised learning, where we might have apples, bananas, and oranges. And the task, instead of trying to assign a label, is to assign or how are these objects similar and which ways are they similar, and to group similar objects together. And again, the machine learning comes up with the program itself. So why do we care about this? Of course, I've alluded to this, but we start seeing more and more high consequence applications of AI machine learning. The recent conflict between Russia and Ukraine have had automated drone attacks. The U.S. similarly is investigating. These are just taken from Google News search. So these are open headlines up here about different military usage, of course, which is a little concerning depending on how far down the Matrix road or Terminator road you want to go with Skynet. But they are starting to become more and more prevalent, especially in military use cases. In addition, as Shinhan also pointed out, they're also an additional vulnerability attack vector. Siri works as it should, but hackers have been able to play inaudible messages to have that do whatever it wants to do, essentially. So again, as Shihan mentioned, data is essentially the keys to the kingdom here. If you can control the data and the input, you can have a lot of control. And even the thought leader, so Elon Musk recently has talked about maybe we should put a halt into our AI development. And if you think about Jurassic Park, the question shouldn't be whether or not we should. It's whether or not whether or not we could. It's whether or not we should do these type of things. So just to, again, point through, one of the reasons it becomes so hard, and from a T&E perspective, even an assessment perspective, is machine learning is not just some simple model at the very end that we understand what goes into it, but it's rather this large process that a lot of information goes through. So this slide up here is trying to iterate this. Oftentimes we have raw data, not often, we have raw data that comes in. And the first step, of course, is how to do data engineering, how to do feature engineering, feature selection. Anyone who's ever done machine learning knows oftentimes the biggest point is not actually the machine learning, it's doing the data cleaning and getting the data all prepared to incorporate. And there's often an iterative process here where a data engineer comes in, talks with subject matter experts, finds out what features are the most important and how to get the data in the proper format such that a machine learning algorithm can actually operate on that data. Once we have that, then you start going down the rabbit hole of picking out the algorithm that you should be using and then setting the hyperparameters that should be used. So if you can think about hyperparameters, for example, in a neural network might be the number of layers, number of neurons per layer, the activation function, learning rate, etc. In a random forest, it might be something like what is the splitting criterion that we're using, or the number of trees in the random forest. And of course, that's also an iterative process. And once we finally get our candidate model, we can deploy that, and it's put into an overall system. This will come back to this later, but the key point here is just to recognize a lot of information goes into developing the machine learning model before it finally gets to the deployment stage. Okay, so we have this machine learning thing. We know how to deploy it and develop it. What vulnerabilities exist? Shihan alluded to this as well, but we have identified, this is a slide I guess we use at Sandia National Labs, 4 main categories. You can think about evasion, subversion, extraction, and misuse. And I'll talk about each one of these, and you'll see some similar pictures because they're popular. So I'll go through this fast. I'll go through this fast, recognizing that I'm standing between you and lunch as well. I don't want anyone hangry at me once we're done. So of course, evasion. This is the wolf in sheep's clothing here. How can I look like something I'm not? The famous picture of the Pan and the Gibbons. I'll skip through that. Subversion, data poisoning is also what it's known, right? So there's a couple examples that Shihan also pointed to, but just to point out, right, the stop sign turns out nice, but these special little characters down here were specially designed and put into the training set to poison the data set. So whenever it saw this little sticker up there, that stop sign became a yield sign or a speed limit sign, which of course is concerned. These are real world attacks that were demonstrated in academic literature. Extraction, you can actually steal information from the machine learning model. It used to be thought of that a machine learning model is essentially like a one-way hash. You took all your training data, you trained your model, and then it was kind of like this black box. It still is a black box, but you can extract out pretty good and well-representative training data. So this is one of the original results, or I guess results for model inversion that was done in 2015. That was 8 years ago. Technology has improved quite a bit in the type of data that can be extracted. Additionally, here you can also extract model parameters, which represents IP. Of course, so if there's significant investments in there, the IP can be at risk because these models can be inverted. And then finally, there's this misuse. And the most popular kind of this misuse attacks are what are called deep fakes. So the example here I have is a comedian, Jordan Peele. He actually starts talking, and if we had this YouTube video up and running, what you can see what he's saying is projected onto President Obama, and he can say whatever he wants, and President Obama in this picture says it right in the video. So this is of course a concern for misinformation campaigns and misrepresentations. Okay, so of course those aren't the only things that can go wrong. There are several that we've seen. So these again ripped from the headlines of news. So recently, Facebook, I guess recently, it's several years ago now, their Tay chatbot. It became hyper racist in the matter of hours once it was released to the general public. Google had an image classifier that was racist as well, purging the label gorilla from its classifier. People who didn't fall into the right demographic were labeled as animals. And then, of course, Tesla with self-driving cars has also had some unfortunate experiences using AI. And one of the key components here is understanding, again, our training data. So this image here I put here on the right here for you of your training samples, that's what the machine learning is trying to use. The green line represents the model that the machine learning algorithm learned, but the red one might be our true function. You can see there's always a disconnect. So there's a saying in statistics that always says all models are wrong, but some are useful. That very much applies here in machine learning. We're trying to understand how do we assess these models now. Okay, so now that we kind of got this understanding, what is machine learning, why do we care, and why is it different how we try to assess these things, what we've come up with is this general framework of how to go through this process. So just real quick to put this up, it changes a little bit here. So I put this up partially for my own benefit. I'm a computer scientist by training, but not a test engineer. So testing, just to I guess set the scope here, I'm talking about assisting risk management, but it's also talking about certain requirements that are specified perhaps in documentation, ensuring that the system meets those, and then validate measurable quantities. So you can think about with machine learning, this might be performance on a validation set, or perhaps certain defenses are in place. We can check the boxes, make sure those occur. When we start doing assessments now, this is like assessing cyber assessment or red team penetration testing for a network, trying to understand, what is the posture, the security posture here, and what are possible vulnerabilities and impacts that might occur to the mission. So machine learning, for example, we want to understand how does it perform on real-world data. If you look at the academic literature, this is a major concern. There's often a major disconnect between what's reported in literature and what actually happens once a system is deployed. And then, of course, there's also vulnerabilities against these possible attacks that I just mentioned as well. So of course, there's lots of tools that do this. I encourage you to attend a talk later on tomorrow. So our colleague Carrie Ann Martinez will be giving a talk on a lot of these tools that are available. But I just want to point out that a lot of these work, but often they're focused specifically on the model. As Xinhan pointed out, oftentimes it's really easy to just get the model directly and not have to worry about the rest of the system. We're trying to look at the entire system, as I point out here. But I'll point out a couple of things. IBM Research has a lot of really great tools for explainability, fairness, privacy, and doing uncertainty quantification. It does require a subscription to be able to use that. But then NIST has some work as well as some open toolboxes that you can use to help with any type of assessments. Okay, so when we go to a system and we're trying to assess something, oftentimes everything still is a black box, right? So I put this diagram up here to show what is often provided to a test and evaluation engineer. Oftentimes we get some documentation, and here's the system. But as I talked about earlier, of course, there's a lot that goes into the machine learning development process. So the one little component down here, which is our data preprocessing, there's this whole box of iterative processes that were going on, as I mentioned before. Same thing with the machine learning component, which represents some little software packages, has all the implications from the training data, the test data, what were the performance metrics, what was the algorithm, what is this, how is it implemented, the source code. Oftentimes that's all obfuscated or not provided to the tester. So the questions that we are starting to answer is how can we start drilling down and understanding and mitigating the risk and testing these systems properly given what information we have, and perhaps asking and requiring more information to be able to have confidence in these systems, especially as we deploy them higher consequence applications. Okay, so that's just what I just said. Next slide. All right, so this might look familiar to anyone who's a red team or done penetration testing. This is the framework that we're following, and the remainder of this talk will go through these slides and talk about how do we adjust each one of these steps, specifically now that we're considering machine learning and AI components. And the key thing I'll point out here is we have a three-pronged assessment. We're trying to understand what are the adversarial vulnerabilities or attack vectors. So this is where I talked about evasion, subversion, so model poisoning, model stealing, as well as misuse. What is the cyber component? I was mentioned before, as Xinhan mentioned, most machine learning engineers don't think about security. They're very much focused on how to eke out the next little bit of performance. Of course, there's also a lot of attacks that can happen just by doing cyber attacks to the system. And then finally, we want to understand how does the machine learning model actually perform once it's deployed in a mission setting. Okay, so first thing we want to do, as is common, we want to be able to define the scope. During this is a very high level. We started with the documentation. How do we go through the documentation to understand what it is? But the key point here, I think, is we want to be able to understand what is the goal of the attacker, specifically with the machine learning model. There's lots of ways that we can subvert the model, but understanding which attack vectors and which is the most important. So for example, perhaps the most important is that we want to be able to share this system, but not have any of our data leak out. Right, so you can think about a repository of malware. We want to be able to share some machine learning based defense to protect everyone else's system, but not necessarily let the adversary know which samples of malware we have seen or have not seen and how we're vulnerable. So of course, there's machine learning and adversarial machine learning SMEs that can help outline these scenarios for this with the stakeholders to understand what the practical consequences and the risks. And again, I put down here for a lot of these things, this is, I guess, a pen and paper exercise to start with, right, to really point out what are the risks and how can we help mitigate these. And when we do our assessments now, how can we address those? Staffing the team, of course, for your typical red teaming team, you'll need some additional expertise here, particularly with the machine learning, the adversarial machine learning. But you also want to be able to have the stakeholders involved as well to be able to bring it all back to how it actually affects the mission. Okay. So again, another pen and paper exercise. Now that we understand a little bit about what the system's doing, we have a basic understanding of what the domain and the threat actor might look like. We want to be able to put this down and start talking about real use cases here, and be able to talk about, okay, now that I know perhaps a different machine learning model, what are the possible vulnerabilities that exist? How can we attack them from an adversarial machine learning approach? Again, most of the machine learning is data-centric, so not only focusing on the model, but now we have the whole system. So what are the touch points? Where does the system come into the data come into the system, and how can we start affecting the data that way? And particularly, how can we affect the machine learning model? And then we want to start documenting the possible types of risks that do exist. And then we can start, again, following the red teaming. How do we interact with the system here? So this is where, this is where the rubber starts meeting the road. We have an understanding of the mission impact that perhaps the machine learning model provides, but also now we have some understanding of where we might be able to start attacking the system. So we want to start scanning and be able to find out what is supporting infrastructure. For anyone who's done some type of assessment of a real world system, often the documentation does not match what's actually deployed. So making sure this all work is part of the purpose of this system here, to understand where can we touch the system, where does the documentation not match what is actually deployed. The machine learning, often we need to be able to detect to see if this actually exists. Again, this is a very strong buzzword right now, and a lot of contractors are willing to put in machine learning anywhere, right, to sell it, and perhaps there might not be machine learning, or the machine learning might be used in a different way than what was expected. So we're trying to do some reverse engineering of where the machine learning is, understanding where that is, and how to actually interact with it. And then, of course, we want to do the recon. We want to understand where are the data pipeline, what are the configuration files, perhaps, where's the model stored. These are, of course, all vectors that an adversary could attack to upset or disrupt the machine learning process. And of course, there's a lot of toolkits. These are traditional possible toolkits. Think about Metasploit, Cobalt Strike that you can use. And once we actually start discovering, this is where we start planning out our vulnerability assessments. We've scanned the system. We've had our documentation, our background, and we're trying to talk about which one has the strongest mission impact. We want to start looking about how can the machine learning model be subverted. Again, looking back to if we want to steal or just evade detection. I want to do a cyber assessment. How can the model be affected through the supporting infrastructure? And I'll talk about one of these exploitations that we did here in a minute, but you can think about, oftentimes we go these very sophisticated methods to try to change the data and perturb it so the human will to recognize. Oftentimes, a configuration file, for example, might not be protected, and you can just change thresholds, which is very easy. And then, of course, the machine learning performance assessment. This is perhaps one of the toughest ones. We want to understand in an unknown environment or a contested environment, how well will the model adapt from being developed in a benign. Okay. And so once we have all of this, of course, now we can do our exploitation stage. This is usually where it's fun. This is what gets published in open academic literature as well as the news articles. We see these fun little pictures. As we walk through this now, we want to be able to document effects of what was able to be affected, but perhaps most importantly, as I mentioned, there's lots and lots of steps that go into machine learning, but we'll document what was not able to be assessed. Oftentimes, if we don't have, for example, access to the training data, you can't do certain exercises. You can't understand, are there biases that the model was trained on? And this is a big problem because most of the companies, their key IP comes from the training data they've been able to provide, or if you're talking with some type of government agency, perhaps, that's also where the highest sensitivities lie. So understanding this and understanding what you're not able to assess because of what you don't have access to is a big risk. And then also make sure we're speaking terms familiar to the customer. So yeah, I'll talk just a minute about this just for, as I guess I alluded to this. One of the assessments that we were doing, we found we're doing a very simple model, so called Gaussian mixture model. So think about a number of different Gaussians that kind of mix together to model distribution. And one of the assessments that we did, just to highlight the cyber concern, the configuration files were not protected at all. And they had two thresholds that configure the whole entire model. And we could, in this case, they're trying to do C2 detection, so command and control. And we were able to just adjust those parameters, and we were able to have our C2 be able to go in and out of the network undetected just because it was a very simple way to get through. The other thing we found was often databases are improperly configured. So Elasticsearch, you had to pay extra money to have security put on top of it. They didn't want to pay the extra money. So again, another easy way to thwart the machine learning just by some improperly configured files and databases. And of course, there's lots of toolkits for this. I think this is probably one of the biggest things that are out there because it's fun. But there's art, privacy toolkits, deep checks. Again, let's go to Carrie's talk. She'll talk about a lot about these. So when we go through these, there's a lot of different vectors, I guess, axes you want to be able to invest, monitor about how, when you talk to a customer, we want to be able to provide a couple different axes along which these attacks are either possible, how stealthy are they, how transparent are they, and ultimately what's the impact on the end analytic. Of course, with machine learning performance risks, I'm going to start talking about what do we have access to and do not have access to. I already talked about these. But a key thing here is reproducibility. Oftentimes, it's really hard, even in academic literature, to reproduce results. But as a test and evaluation community, it's essential that if the developer reports some type of results on the machine learning model, we should be able to reproduce those as well. And then cyber risk, of course, I just mentioned some of these. And finally, this all comes back right into our final impact analysis. So this is where everything coalesces back together. The whole team comes back together, and we need to make sure that we can have our powwow to understand. We've done all of our assessments. These are the CAML, or the adversarial machine learning assessment risks, the real world risks, as well as the cyber risks. And present these and have a nice talk with the end customer and outline any possible remedies that we have there. So this is our basic framework. You can see that most of the steps are fairly straightforward from what we had used before. We've done a number of these assessments, which I'm happy to talk about offline if anyone has additional questions. But that is of course, our presentation. We live in a world where we do need machine learning. Machine learning does provide a lot of very exciting technologies that will help in a lot of different ways, right? We can't scale with the amount of data that we have to go through. Our other, let's just say, competitors are using machine learning in lots of different ways, and we can't afford not to use machine learning. But be aware, they do come with a lot of risks. And it's our role to be able to trust the algorithms that are being deployed and the systems in which they're being deployed in. And this is an untapped area right now, as most, again, the academic and open communities focus just on the model. But there's a whole system level that I think that this community is well suited to address. I think that, yeah, that's it. So thank you for your time.
Questions? So I have a leading question.
Sure.
So you discussed you discussed things that are off limits or things you can't access, right? And so as you're working with the rules of engagement, do you have a way to convey to the customer what they're not going to get by excluding part of the scope of the test? That's something that we have challenges with in terms of testing the entire system versus testing the one little piece.
Yeah, so that's a good question. The way I put this here, and the way I think you're trying to ask this, is like, which components of the machine learning model do we have access to? So if we don't have access to the training data, for example, that limits, again, a number of different things about privacy and bias concerns that we currently don't have. And we are currently putting together that framework right now.
We share that.
Yes.
Any other questions?
So it's pretty straightforward to interject machine learning into existing systems. But as you describe, it comes with some intended responsibilities that might be overlooked. Have you thought about how to articulate, kind of like, if you will, a cost and complexity penalty for interjecting machine learning into, say, a mature product?
Yeah, that's a good question. So there's actually quite a bit of research. The key term you're looking for is called technical debt, if you're familiar with that. So as you put in machine learning, there's obviously the uptick of how do we make sure it stays up to date. We understand what it's doing, and then the technical expertise that goes into that. Does that answer your question? Yeah.
Anyone else? Well, thus endeth the session. Thank you everyone for coming. Let's thank Michael and all our speakers again, please.